Welcome to today's session of the lecture series on fluid inclusions in minerals. We shall continue our discussion on the techniques of in situ non-destructive analysis of fluid inclusions, micro analysis of fluid inclusions, and we were at the middle of our discussion on the one of the techniques which is very widely used by many fluid inclusionists across the world, and is a simpler technique, but a powerful one, that is the laser Raman microspectrometric analysis, or LRM as we call it. So, just to recapitulate what we are discussing, that when we subject an inclusion which we have to choose under the microscope at a suitable magnification, and then select the inclusion which will be at a particular focus from the surface of the wafer. This individual inclusion has to be focused so that the laser light is also focused on the inclusion cavity below the surface of the wafer, and then we expect to get some peaks at corresponding Raman shift, and those peaks would be characteristic or the fingerprint of the molecules, gaseous species, sometimes the solid crystal daughter crystals, or sometimes when the spectra is being taken at a very low temperature, which we will be discussing subsequently. So, we get a multiple of peaks corresponding to various values of the Raman shift, which is nothing but the difference in the frequency of the emitted light with respect to the incident laser frequency, which we know that we are using a monochromatic laser light of a chosen wavelength. And so, let us have a look, let us recapitulate that we discussed on this particular diagram with respect to a linear molecule which is carbon dioxide, where the number of fundamental vibrational modes will be 3 n minus 5, and so there are 4 vibrational modes, or 4 vibrational the frequencies, and corresponding to a symmetric stretching, bending to 2 modes of bending, and asymmetric stretching. Just to put it in a more definitive way, if it was not clear before, that this kind of diagram, which is constructed from the classical mechanical viewpoint, essentially will is giving us some guidelines, and that which of the fundamental vibrational modes will be Raman active. So, when we take this diagram, they take the value of alpha 0, where the derivative is the derivative of the polarizability alpha with respect to space, and when the spatial displacement is 0, the value corresponding to alpha 0, and the derivative at displacement 0 will have some finite value, and that would correspond to an active Raman band, Raman vibrational mode, in which we would expect to have a peak on a spectra which will be Raman shift versus intensity. As against that which is symmetric, all the other cases of an asymmetric stretching or bending, there the derivative at displacement 0 will have a value of 0 as shown on these 2 diagrams, and there the derivative at displacement 0 is equal to 0, and there these modes will correspond to Raman inactive modes, and in which we will not be getting any peak. So, these provide us some broad guidelines and some basic understanding about the use of Raman spectroscopy in characterization of the molecules that are present in a fluid inclusion, they are in liquid state or vapor state, that does not matter, and as long as they constitute of molecules in which there are covalent bonds, they will always be, and some of those such Raman active modes will always be reflected as having peaks. But then actually in reality, what we get, that sometimes we get many number of peaks. Say for example, in case of carbon dioxide, when there is only one mode which is supposed to be Raman active, but on a spectra of carbon dioxide we might see more than one such peaks. So, many such peaks we will get, as you will see soon. Some of them may be because of the hot band. So, this hot band is nothing but it is centered on a hot transition, that is a transition between two excited vibrational states when no one is in ground state. So, these are some of the intricacies of the interaction, the spectroscopic intricacies of the spectroscopy based on very fundamental physical principles, which we will not be discussing here in details, but they will be only of practical utility to us. We get sometimes in a molecule like carbon dioxide, instead of one we get a diode, which basically is called a Fermi diode. It is a consequence of quantum mechanical mixing, and sometimes on a Raman spectra, for example, we take a silicon and try to take a spectra. In addition to the very prominent peak corresponding to a Raman active vibrational mode, we sometimes also get peaks which are called as the resonance peaks, and there the incident electromagnetic energy is close to an electronic transition. So, these are some of the simple things which always be kept in mind while taking a Raman spectra of any particular inclusion. So, here such kind of microscopic arrangement when a microscope, when a laser Raman spectrometer is coupled with a microscope like a normal polarizing microscope which we use in routine petrography geological applications with higher magnification, sometimes 500 or 1000 time magnification, because sometimes we need to have the laser beam focused on a very small diameter, and also when we are trying to examine or characterize an inclusion which is very small, and yet we would like to put the laser beam on a particular part of the inclusion, there sometimes we take it in a higher magnification. Higher magnification, use of higher magnification also sometimes has for much better quality of spectra that we need to take sometimes. So, with this now let us try to look at that how the Raman spectroscopy is used in fluid inclusion research. As is said in the context of Raman spectroscopy, that Raman spectra of a particular molecule is its fingerprint, means we would possibly say that if there is a molecule like methane and then its Raman shift, we would expect, or it's as it is documented in books or in standard literature, that we should get a peak around 2914 centimeter inverse. But then this Raman shift or this the Raman activity of this particular covalent bond which is there in this methane will always be a function of the atomic environment in which it is present, and also the density of the particular gas or the particular gas the molecule is in a liquid state. The density also is a function, it also decides the precise position of this particular peak on a Raman spectra. Even though it will not vary in very great ranges, but here there is a diagram which you can see here. There is a total pressure in bars versus this nu 1 of methane, this Raman active mode of methane, which generally should be expected around 2914, can vary from as a higher 2916, 2912 or 2910, depending on what is the pressure. So, as pressure is increased, means density is higher, we would expect the Raman peak, the Raman shift to be occurring as lesser and lesser difference in the frequency or in a spectra towards the lower value of Raman shift. And this is shown on a CO2 and CH4 and N2 mixture. When it is 50-50 N2 mixture, we could see that when it is present in a mixture in a different atomic environment, when it is not pure, there also there is some shifting of the peak positions on a Raman spectra. They have been used, or they can be theoretically they can be utilized to talk about or to estimate the density of the liquid of the methane which is present sometimes in mixture with carbon dioxide. It should be possible. So, it is just to show that even though we take it for granted that Raman peak position should be a fingerprint of a molecule, but we should not expect any particular molecular species to be all the time abiding strictly by that principle and get to expect the peak to occur exactly at a very fixed position. Well, this is coming to one of the one of the important utility of Raman spectra, which is being practiced in by many laboratories, by many workers. So, the question that is it possible to have some kind of a semi quantitative idea about the composition of the material, or the liquid or the gaseous or the gas in a vapor bubble in a inclusion, or the liquid part in an inclusion. Take it for granted that suppose it is a carbon dioxide and methane mixture. So, if it is a carbon dioxide and methane mixture, if there is no other species present, is it possible to determine the proportion of carbon dioxide and methane, because as we saw before, when the carbonic inclusion which is there in a sample is not pure, as indicated by its depression in the triple point from minus 56.6, we suspect that there is methane, and from the melting point temperature of the solid carbon dioxide and the partial homogenization of the carbonic phase by intersection of the curves which we saw before, we can have a rough idea about the mole percentage, or in terms of mole fraction of methane in a carbonic inclusion. This is also possible if we have the Raman spectra. Say for example, here A and B is the peak position of two species. Let us say A is methane and B is carbon dioxide. So, is it possible to have some kind of an idea about the proportion in which they are present? Some very simple, although this kind of, here we see there are 3 or 4 parameters here. The A stands for the peak area of A and B. So, C is essentially the concentration of A and concentration of B. So, that would be related to parameters which is shown as here as a sigma A and sigma B, which is known as the Raman scattering cross section. This is a fundamental parameter of particular species. They are wavelength dependent. We have in standard literature the tabulated values of the Raman scattering cross section at different wavelength of lasers. Say for example, 514 or 526, 785, or there are many wavelength lasers which are used starting from the UV to IR ranges, and those values are tabulated in standard literature which you can get. Suppose we want to determine the proportion of methane and carbon dioxide here, we can calculate the area of the peak by standard method of peak integration, or which if you are using a software, there are very popular and accessible softwares which will be doing the integration for the peak from the graph. So, if we calculate the peak area, so that peak area is going to be proportional to this ratio, and here the other parameter is sigma A and sigma B is sorry Xi A and Xi B is basically is something called the instrumental efficiency of, or instrumental sensitivity or instrumental efficiency is whatever you can put for that particular species. So, when we are getting the peaks of methane and carbon dioxide, this peak that we are getting in the machine that we are using, this parameter has to be determined. So, what is exactly done is that if we have some standard material with variable concentrations of methane and carbon dioxide, so some such synthetic fluid inclusions or natural fluid inclusions where the concentration has been measured by many different laboratories, and a value which a known value is agreed upon that this particular inclusion or a series of such synthetic inclusions, or even a gas mixture, even if it could be done in a pressurized gas chamber where we can take different proportions of the two gases and take the Raman spectra, then it is possible to have such kind of standards, and for any instrument that an individual is using, this instrumental efficiency parameter for this gaseous species, or for that matter many gaseous species, could be known beforehand. So, therefore, it is possible to calculate the concentration ratio of these two species that is present in a inclusion fluid. Sometimes it so happens that suppose we are measuring, or we were interested in determining the composition in terms of the concentration ratio of two gaseous species like methane and carbon dioxide, and as we just discussed, and we will also see in the subsequent slide, that carbon dioxide will have more than one peak corresponding to the Fermi diode, one at 1285 and the other one is 1388. So, it will all become a matter of choice that which particular peak is to be considered, or whether both the peaks can be considered with some kind of an averaging. the practice has always been to, in case of carbon dioxide, to choose the 2 peak, that is at the 1388 centimeter inverse, and then take the peak area and then ratio of the peak area to a methane peak, and then calculate this particular ratio. Sometimes it also we might ask ourselves, is it possible that the Raman spectra can be used for analysis of the inclusion in bulk? It means the thing is that inclusion in bulk means you can think of the situation where the inclusion is homogenized. So, suppose for example, I have a aqueous carbonic inclusion where this is the aqueous liquid and this is the carbonic liquid, and the carbonic phase partial homogenization has taken place, and this particular inclusion is now homogenized to one liquid. Let us say it is homogenized to aqueous liquid. So, now this essentially is a homogeneous fluid here, and it does not matter where the laser spot is put, here or here or here. So, it will give the same composition for this particular inclusion, but then this particular homogeneous state is only attainable at a particular temperature. So, there are some workers who have used this and measured taken the Raman spectra. So, here also when we, if this is a aqueous carbonic fluid inclusion which is homogenized, so it has H2O and CO2 in it. So, if we take the Raman spectra of this, we are supposed to get the peaks of H2O and CO2, and we can use the same the workers who proposed that, they have fit an empirical equation to the ratio of the peak area of these two species H2 and CO2, but it will always be applicable to the measurement could only be, or the whatever equation is proposed will be applicable only to that particular temperature. So, such situation as and when it is so theoretically it is possible to estimate the bulk composition of a particular inclusion in terms of the proportion of this species, at least a very simple case when it is aqueous carbonic inclusion and water and carbon dioxide, and if it is taken at a higher temperature, only these two molecular species could be identified. There we will not have much idea about the effect of the salinity of the particular aqueous component. So, this is even though not very frequently used in literature, but some such possibilities also exist, and it is just for the sake of the completeness of the information that and also it is an interesting situation where there was some work one particular piece of research. It attempted to estimate the salinity of the aqueous phase by taking the Raman spectra of the aqueous liquid at, it could be just at normal temperature. We know that in normal that the water will have its peak because of the OH stretching, the molecular vibration in the O and H, and the diagram here it shows the first black line corresponding to pure water, which is 0 wet percent NaCl, the red, blue, green and the purple curves correspondingly are representative of the aqueous liquid at 5.5, 10.5, 19 and 26 wet percent successively. And as you could see here that the peak center position of the peak seem to be shifting towards higher wave number with increasing wet percent of salinity. So, the question is even though we definitely have a prior idea about the salinity in terms of wet percent equivalent from the freezing study, but we know that it is giving a cumulative effect, and if we want to calculate the again in the to corroborate it or to exactly to have a better idea, we can use this. So, this particular peak of water, the Raman spectra of this water, unlike what we see in some species like carbon dioxide or graphite or methane, which we have seen earlier, does not occur at a very sharp peak, but it occurs as a broad hump almost like from 2800 centimeter inverse to 3800 centimeter inverse. And what is generally observed here is in this particular the way it has been applied, that right about 3300 centimeter inverse, all these peaks have a common intersection kind of a point. And as you could see here, the higher NaCl weight percent liquid has a broader hump corresponding to fluid with lower corresponding to water, which is lower NaCl equivalent weight percent. So, these several parameters have been derived here, like if we say the area of the peak which is integrated from 2800 to 3300, let it be represented as x, and 3300 to 3800 if it is represented separately as y, then we get a symmetric a parameter which is x plus y by 2, and then I get a parameter which is asymmetric is y minus x, and then the ratio a by s gives us a parameter z. And here from literature it is the parameter, that means the intensity, the peak intensity is 3400 and intensity of 3200. The ratio is taken to be a parameter which is important for a saline aqueous fluid. And then this parameter, which is a function of this y by x and r, and finally in this particular hump, what we can a parameter which you can think of is a skewing parameter. That skewing parameter is dependent on this all these parameters that we have considered as the ratio of the symmetric and the asymmetric, the difference, as well as the ratio of the intensity at 3400 and 3200, and a parameter d. So, if the diagram on the right hand side, it just gives that, although I have not plotted the exact value the exact species of the electrolyte here, but all these electrolytes like sodium chloride, potassium chloride, magnesium chloride, iron chloride, they will all follow a situation where a skewing parameter is directly proportional to weight percent equivalent in of the aqueous component. And when we calculate the skewing parameter from these fundamental parameters, then the salinity is a direct function, is a linear function of this skewing parameter. So, it is possible that the weight percent equivalent of the aqueous component can be estimated from Raman spectra to corroborate the data that is obtained from the freezing experiment in the fluid inclusions. This is just since we are considering the microanalytical non-destructive technique, we could see that all these possibilities of what people have attempted so far, so that it gives us an idea that in which of these methodologies it could still be improved to get better results, and also making this technique a more useful one. And already this Raman spectrometric technique is widely used. Some other kind of special features that you could see with Raman spectra is here, which is it is of course far off to say that actually they will be indicating the isotopic ratio in the carbon dioxide that is present, but for the sake of our understanding and as an information, it is very interesting to see. This is the spectra of carbon dioxide. This is occurring at 1285, this is the nu 1, and this is the 2 nu 2, that is 1388 centimeter inverse, these two commonly known as the carbon dioxide formidiad. So, what we see here, as we discussed just before, that we see a lot many more of other different types of peaks with variable intensity at different positions of central Raman shift. For example, if we take carbon dioxide, then in case of carbon dioxide, in the nu 1 peak, just before the nu 1 peak, we get one hot band, as we know that the transition between the two excited states of two vibrations at a excited state, and that is 1388 peak also to the right, that is one hot band. But interestingly, to the left of this 1388 peak, we get one small peak, which is essentially due to the 13 carbon. In sometimes while taking Raman spectra, we do observe, in most of the cases we do not, and as it is been suggested that this particular the presence or the prominence of this particular peak is depending on what is the concentration, or what is the, as we express that what is the del 13 C value. Sometimes it is put at about 20 per mil or 27 per mil. If it is less than that, then this peak will not appear. As it look like, it does offer some promise that it may be that if this technique would possibly be further enhanced by taking the Raman spectra in some special conditions, for example, integration of very long time, and using some technique, if this kind of peak could possibly be retrieved, then we also do get some idea about the isotopic ratio, or what is the proportion of 13C that could be present in the inclusion fluid, and we all know that is a very important parameter. And sometimes there are laser induced transformation. The laser spot, when it falls on the material, it generates a lot of heat, and that heat could be calculated, because it depends on the laser wavelength and also depends on the laser diameter, and this kind of exactly in terms of the heat generated can be calculated, and we know that this heat is pretty significant, and sometimes they may cause laser induced transformation. They are not of much use as far as fluid inclusion research is concerned, but sometimes this kind of laser spot induce in a carbon dioxide and methane mixture, they do result in instantaneous formation of graphite, which is reflected or which is expressed as a in the Raman spectra. But we will be discussing exactly about the origin of graphite in a later section. Even and this, as far as this diagram is concerned, which is coming from Wang et al. 2011, we see here that the density of carbon dioxide varying from almost like 0.2, 3.2 or almost 1.4, and if we see this difference between the Fermi diode in terms of the value, what we get is varying from 102.5 to 106.5, and this difference in the Fermi diode is also an expression of the density of the carbonic phase. So, Raman spectra in a way gives us a lot more of information, and it could still be further worked upon to get many more of such information from the Raman spectra. The density of the carbon dioxide also can be obtained if we have use and see such kind of diagrams, and then finally we look for an equation which should relate us the density to the difference in the Raman shift between the two Fermi diode and carbon dioxide. Let us just quickly, although it cannot be, we know that it cannot be exhaustive, but let us quickly look at some of the points, because knowingly I am giving a bit of emphasis on this particular micro beam technique, because it's the instrumentation is very simple, and any fluid inclusionist with a bit of a interest in instruments, handling of the instruments, can easily use or can easily handle an equipment, run the equipment to get Raman data, Raman spectroscopic data, and can. So, here some of the frequently asked questions, that which laser wavelength to use. We know that shorter is the wavelength, it is definitely high energy of the laser, but sometimes high energy also is a little bit of disadvantage, because if the material is highly fluorescing, then it is always advisable to take a longer wavelength laser where the fluorescence is minimized. And so, depending on that is the reason why sometimes during the sample preparation also we have to take some extra care, that the kind of mounting media that we are using should not be fluorescing, or even if we are using that mounting media, it is always advisable to take the wafer out of the slide on which it is mounted, and before we go for taking the Raman spectra. So, wavelength selection is depending on that, and definitely the signal will be always better for a shorter wavelength and a higher energy. For example, if we compare between a 514 nanometer green laser or a 785 IR or red laser, then it is always the shorter wavelength laser will always give better signals. So, what are the other problems generally we encounter while taking a Raman spectra? Sometimes the fluorescence, as I said, it always gives us a very noisy baseline, sometimes rising baseline. It is because of the fluorescence, even the material which is present within the inclusion cavity or in the host mineral, there are so many interferences. Sometimes we get strong interferences from cosmic ray, and it generally the software, there are provisions to get rid of this kind of cosmic ray, or even manually it could be removed. And sometimes if the because of ignorance, if we have a lot of light, so that is the reason why a Raman spectroscopy is carried out in either in an enclosed space without any outside light, or essentially in a dark room. So, if you have extraneous light coming, it will interfere, and because the kind of detectors which are used here are so sensitive that any amount of extra light will always saturate the detector and the signal will be lost. So, is it possible to analyze aqueous species inclusions by Raman spectrometry? The answer is yes. It is actually the cryo-Raman. When we when we freeze the inclusion to very low temperature, almost like 180, very nearly to the liquid nitrogen temperature, because at that type of situation where we can get the Stokes side of the spectrum more clearly, and we also do have the provision that the same setup on which we are the spectrometer and the microscope are coupled, we do also have the the stage like a Lincoln stage mounted on that. So, we can take the Raman spectra when the temperature is very low. So, it is basically known as the cryo-Raman spectrometry. So, sometimes we may not get the Raman peak at the expected shift as mentioned in the literature. First, we have to see that whether we have properly focused the inclusion that we wanted to analyze. The laser alignment is also another important factor, and today's most of the present day equipment do have automatic alignment systems, but the old one where the manual alignment has to be done. So, their laser alignment is one of the problem, and peak shifting is also one of the reasons. In such kind of systems, we use standard material for checking the calibration or the peak positions. For example, a silicon crystal is used to check whether the Raman shift is coming exactly on the same position as expected, and there are this instrumental parameter could be adjusted to get the known peak at the proper position, and if that is so, then we would definitely get the desired signals at expected peak positions as mentioned in the literature. Raman mapping and imaging are essentially done for solids, very rarely for inclusion, but still could be done. So, Raman mapping is essentially by taking a lots of scans on lines, take the Raman spectra and reconstruct the Raman spectra in a 3-dimensional manner, all the peaks, or imaging is essentially in a kind of concentration map that can be obtained, and it's could be still done for the fluid inclusion, but as you know that they are essentially homogeneous, the situation or the need does not arise commonly. So, the peak is shifted to higher or lower Raman shift as it can always be there because of the instrumental parameters or the reasons that we have shown. For example, like methane peak can always shift depending on the density, and as well as the carbon dioxide peak, and sometimes when while taking a Raman spectra we may see that there is no peak coming, only a baseline is showing. So, it generally happens when the Raman intensity is so high that the detector gets saturated and it does not show any peak. So, those kind of situation, many of the even these machines which are available in the present day in the market will always have provisions to have the laser intensity decreased either in a very continuous manner or discrete. For example, a laser light could be reduced to 50%, 25%, 20%, even up to 1%, depending on the material. If the fluorescence is very high, then sometimes we do work at a much lower intensity than the full intensity. For example, a 20 milliwatt laser, so the intensity we can reduce to almost even 1% of that, and the peak positions does not match with any commonly known gas, molecule or solid. So, this is a situation which can happen if there is some material or some compound or some gaseous species which is there in the inclusion fluid, but there are Raman libraries. So, generally this point I have mentioned keeping in mind that many of us or many people, many of the inclusionists who are having a Raman system, if they do not have a Raman library inbuilt, so then this searching of the library to exactly to see which molecule with this particular spectra is matching, and sometimes the baseline is also very noisy and erratic, which could happen because of extraneous light or could be fluorescence, and they could be manually or using some software the baseline could be corrected. And as the last point, the Raman peak may not always be very sharp. For example, the resonant peaks are generally broad, and sometimes as we see inherently water gives a very broad hump rather than a sharp peak. So, these are some of the frequently asked questions, and I know that it cannot be an exhaustivity of questions, and I still would like to answer any such questions which they come up in the forum later on. So, we conclude our discussion on the Raman spectroscopic technique. We will continue in the next class. Thank you.